Hello everyone, my name is Wong Zixuan, or you can call me Zixuan Wong. Today I'm going to introduce my special project. The first thing first is that rain itself is a really common thing, noise in our daily life. And rain induces multiple degradations, and this kind of degradations will do some harms to some downstream work, like you can see in some prior works or on experiments. Yes. And also this kind of degradation is really various, like having splash, welding, and streaks. And one of the challenges is that if we do the single image method on each frame, it will cause some temporal inconsistency, which we will see later in the visual comparison. And another thing is that the computational cost is often large in this kind of deraining research is because most method uses transformer or member. And another thing is that rain patterns is really diverse because, like I mentioned, rain itself having multiple degradations, and also one path is enough, not enough for the rain for this kind of noise. Another thing is that the real world scenario still remains some domain gap between the data and the real world scenario. Yes, obviously. So our method, we use a really lightweighted backbone, mostly CNN, not transformer or something like that, something else. So we have two paths, which is about image restoration and temporal. So the temporal can help us to first, it can compare the frame to frame to see whether we have to do the compute again or not. So it can save some costs because RAM itself is constructive, it's continuous, it can be predicted, and the noise in each frame is not really that much difference. So we use the reuse way of catching so that we can save a lot of computation. Another thing is that we use MoE, we use mutual experts, we'll call it MoE later, so that this multiple expert model can handle multiple degradation, reintegration, while for each time we don't even need to use all the model, all the experts, so we can select a few to save some computation. And also the temporal routing also help us to remain a temporal consistency, which is important in the video. And for the instruction, we use a really lightweight refinements head. So the workflow is like this. We have an input and being through some pre-process, like resize if needed, and being through the model. Boom, you got the output. It's a clean video. And this kind of video goes with some downstreams like tracking. It's really important in some autonomous driving or some other like driving scenario or something. And yes, our method achieves a really competitive results, like achieve state of art on some certain data sets. We will call state of SOTA later. And compared to some latest method, our model still remains a really competitive resource. And on the efficiency side, while the others is train and evaluate on a more powerful GPU, still our models like compared to some really efficient SOTA model, we like reduce 70% of the model size and having 4 times faster on the efficiency speed. And for some visual comparison on some common scene training data sets, we can see that our models performs better while the latest range method we can search for is not that great, while it suffers with some temporal inconsistency. Also, we deploy the model on the edge device, which is called NVIDIA JSON or Nano, to test the efficiency, like to simulate the dash cam scenario. We will see in the live model. Okay, here we go, a live demo. we use the pre-prepared scripts. What is script will do is that it will select a clip from a data set which called VRDS, which is a driving video, and it will send one of the clips to the Orange Jensen Nano to do the deraining, and after the deraining, it will also do the detection on it, and after all of this, it will return the picture like this. As you can see, although the deraining picture is not perfect because of the domain gap, the detection definitely becomes better. So after the live model, here's the end of my introduction. You can reach me with the Gmail.